right. Hey there, everyone. I'm going to be telling you about some work I've been doing in the field of star formation, specifically protostars, young stars that have outbursts or tantrums, sort of like some of the very young people you may know in your life. Now, why do we care about protostars and how stars form? This is a big reason for it. I'm not going to tell you too much about exoplanets, but these are exoplanets, planets that have been detected around stars elsewhere in our galaxy. This is just an artist's conception of them, but in your next talk, you're going to hear some things about real exoplanets that are being discovered. But there's just this huge diversity of exoplanets in our galaxy, different sizes, different masses. Some of them orbit very close to their stars, some of them a bit further away. And to explain where all of these planets come from, how all these planets form, we have to understand how stars form. So I'm interested in how the stars that all of these planets orbit may have come to be. This is a picture of where stars form. This is something called the Pillars of Creation. It's an image made by the Hubble Space Telescope. It's something I work on every day. And it's part of a much larger region called the Eagle Nebula. So this is a dark cloud of dust and gas in our galaxy. And in the cloud, you can see some of these little points of light. These are stars that we're seeing through the dust. These regions are cold. Not much light can get in there, not much heat can get in there, and they're pretty dense. There's a lot of matter in there compared to just random parts of space. So when one of these clouds has enough matter, it starts to collapse. It gets smaller under its own gravity. And this is a little schematic showing how star formation works. First, we have this dusty cloud that collapses, and as it collapses, it's spinning a little bit. So it makes a disk. If you think of somebody tossing a pizza in the air to get it to flatten out a little bit, you get it spinning around a little bit. So these clouds form disks. And as the star gets older, that envelope around the star clears away. Some of the material in the disk gets shot out in different directions in what we call a jet or an outflow, and that clears away the cloud, and that's part of what brings an end to the process of star formation. After about 500,000 years, you're left with a star and a disk. And then a lot of these disks have gaps carved out in them that might be due to planets. So we think this is the era of planet formation. After about 2 million years, the disk is usually gone, and you're left with just a star and some planets. So that's kind of an outline of how the whole process works. This is a gallery of young stars. Before I showed you drawings, but these are actual pictures of protostars. So these are stars where they still have a disk and an envelope. And these are all obtained by the Hubble Space Telescope, shown here. Most of these are edge-on systems, so what we're looking at is really like the edge of the disk. So the disk blocks out the starlight, but then we see this fuzzy nebulosity around the disk. And that's part of the envelope that's being lit up by the light from the star. That light gets scattered off the dust and gas and comes toward our line of sight. So we have some of these. This is one of my favorites. It's got just kind of these two little bits of nebulosity and then this kind of hourglass shape. Here you see one of those jets that comes off the star that I was telling you about. And you've got just in some cases, there's maybe just like a single little blob. In other cases, they're about the same brightness. This one's got these kind of weird arc-like structures that we have to figure out where those came from. There's like a ring-like protostar nebula here. So there's just a lot to figure out here. Protostars are sort of messy. They don't have like simple stories. Each one's got its own story, really. So I study star formation in the constellation of Orion. And here's just a drawing by the astronomer Johann Bayer back in about the year 1600, illustrating all the brightest stars in Orion and showing you the Hunter. So some of the famous stars are visible here. And if we look at Orion just with a basic visible light camera, we see some of the famous stars. You might know some of these stars, in fact. We've got Betelgeuse up here, the shoulder of Orion. This is a bright red star. It's a red supergiant that will explode sometime in the next million years or so, give or take a few. Down here is Orion's knee called Rigel. There are other bright blue stars. These are young but very massive stars, so they're only going to last a few million years. Here in Orion's belt, Orion's sword is here. And if you look here, there's a little faint fuzzy patch. It's not really a star at all. It's really one of these stellar nurseries where stars are being born. It's the Orion Nebula. And here's what happens if you look at Orion not in visible light, but in infrared light. Star formation is kind of an infrared field. We use light we can't see it with our eyes. Its energy is just a little bit too low for our eyes to pick up. But when we look at infrared light, we're seeing the cold universe, these dusty star-forming regions. And here we can see that there's a lot more to Orion than meets the eye. The Orion Nebula is suddenly this bright, glowing patch of nebulosity. But besides the Orion Nebula, we have infrared light all up and down the constellation, showing us the sites of star formation. So this is why we study Orion. There are stars forming all over our galaxy, mostly in the galaxy's spiral arms, but Orion is a fairly nearby example. It's about 1,500 light years away, which is close as far as stars go. The Orion Nebula itself has thousands of young stars in it. It's just the centerpiece of this molecular cloud complex that goes all up and down the constellation, forming thousands and thousands of young stars. It's really the place to go if you want to understand how individual stars are collapsing from their clouds to form sun-like stars and planetary systems. So this is our team, or a picture of part of our team, from the Herschel Orion Protostar Survey, or HOPS. So we've got some hops here that brought you many of the beverages you're now enjoying tonight. This is our team at a conference in Granada in Spain. And it's the Herschel Orion Protostar Survey because the centerpiece of our work was the Herschel Space Observatory. You might not have heard too much about this, but it was launched by the Europeans in 2009, and it operates at very far infrared wavelengths, out where the cold dust that's forming the protostars glows brightest. Herschel is like all infrared telescopes. You need some sort of coolant to keep it at a low operating temperature. That coolant ran out in 2013, so it was a 4-year mission. We got all the data we could out of it. We're still analyzing it. It was really a follow-on to a Spitzer study of Orion. Spitzer was a U.S. project for the most part. It launched in 2003 and had 6 years before coolant ran out. It's still sending back data, though, just not as sensitive data as it previously did. We also use the WISE telescope. WISE is just a little guy. It's the Wide Field Infrared Survey Explorer, and it orbits the Earth and continues to take pictures of the sky. It's now being used to try to detect asteroids that might be headed our way, so we can try to do something about them if the need arises. So we used all these different infrared space telescopes to understand star formation in Orion. One of the things I've been studying in a lot of detail are these outbursts in young stars, these protostellar tantrums that I told you about. This is an image of a group of young stars, not in Orion, but actually in the constellation Cygnus, but it's a really good illustration of how these outbursts are normally observed. This is a picture of the field in August 2009, and then by July of 2010, that particular star had started to get brighter. Here it is in August of 2010, and by September of 2010, it was much brighter than anything else in that field. It was undergoing an outburst. This is where the brightness of the star gets 10 or even 100 times brighter in just a span of months. So we have to understand why this happens. This is just some output from a simulation by a couple of astronomers to give you an idea of what's going on in these stars and their circumstellar disks to cause the outbursts. As these disks get more and more massive, they become unstable. That's really just a way of saying that they break into clumps. So clumps and all kinds of structures can form in these disks. And if you look at the structure with that green circle around it, one of these clumps, these are model pictures over the course of a few thousand years. And this clump starts kind of orbits around, but as it orbits, it's getting closer to the star in the center. And here, finally, by the last one, it's about to fall into the star. So we think that's how these outbursts happen. One of these clumps in the disk falls into the star. And when a lot of mass falls into the surface of the star, it's got a lot of energy in it, and all that energy gets released as light at all different wavelengths, and that's what gives you the outburst. This is an actual image of a young star, and the technology isn't quite there to show us this sort of thing happening yet, but you can kind of start to see these clumps and these like partial ring-like structures that might correspond to what's driving the outburst. So we're really at the beginning of an era of technology where we can see these disk structures and start to think about their implications for star formation. One interesting thing about these outbursts, that meteor back at the bar that you can check out at some point while you're here, we think that all the extra light that comes from these outbursts and all the extra heat actually plays a role in processing the stuff in the solar nebula, in the disk around our own sun. The sun probably had some outbursts like this in its early history, and all that extra heat and light processed the disk material in ways you wouldn't have otherwise, and might give you crystalline structures that you could find in meteorites. So to look for outbursts, we compared two images of Orion, two pictures of Orion. There's this one obtained with Spitzer in 2004, and this one obtained with the smaller WISE telescope in 2010. And we really just looked at one image and then the other to see, are there any stars in this image that became much brighter in the intervening 6 years? And we can look at what fraction of those stars became brighter and get a sense for how often this happens. Here's one example. This is HOPS 223. Unfortunately, these protostars are just have kind of boring names. It's just hops and then some number from the survey. The top three pictures are all from Spitzer before the outburst. You can see HOPS 223 here. Here are some other protostars, and it's kind of about as bright as the one to its south in those two, and fainter in this, which is a longer wavelength image. Here's the after images from WISE, and in all three panels there, it's the brightest one in the field. So that's what an outburst looks like to us. We just find a protostar that got much brighter in the intervening 6 years between images. After we knew about the outburst, we got an image of it with Hubble, and here's the HOPS 223 outburst as seen by Hubble. A lot of these outbursts have these kind of messy, fuzzy nebulae around them. So that's something we look for. We think that all the extra light and heat that comes from these stars kind of interacts with the surrounding dust cloud and brightens it like that. Another one we found was HOPS 383. And this one's got an interesting story. Emily, who was up here at the beginning of the hour here, she was an undergraduate working with me at the University of Toledo, and she actually discovered this outburst, this HOPS 383. She was working on her senior thesis a few years ago and found this. And again, you can see the before images. It's barely even visible to Spitzer at the shortest wavelengths, and just this little fuzzy blob here at the longest wavelengths. And then when we went back and looked with WISE, it was just like, boom, there it is all of a sudden. It's totally the brightest thing in the field, and it just completely caught us by surprise. One interesting thing about HOPS 383, the fact that you can barely even see it here, that means it's really buried in that cloud. It's still got that dense envelope surrounding it, like the first picture I showed you in that series of cartoons. It's the youngest outburst, we think, that anybody has discovered. So it's a sign that even at very young ages, just in the first 100,000 years of star formation, these protostars are going into outbursts. This is a different type of image. These are both obtained by radio telescopes. So instead of like listening to radio waves, we can detect them and make images just like we can with optical or infrared light. These two radio telescopes, JCMT and APEX, JCMT is high up on Mauna Kea in Hawaii, and APEX is in Chile. So you want to put these telescopes at high altitudes in the desert where there's very little water in the air. And what you're looking at here is the cold dust surrounding HOPS 383. Here's the before picture where it's pretty unremarkable, and then in the after picture, it's really brightened up a lot. So all of that light and heat coming from the central star has brightened up the surrounding region. And that's a sign that this really is a very young star, and that really is extra light coming from the star. There are other reasons you might see a brightening, and we can rule them out by looking at this dust image. And this HUPS 383 was such a young protostar and really remarkable and unprecedented that we got a NASA press release out of it. So here's the region that HUPS 383 lives in, and they said NASA satellites catch a growth spurt from a newborn protostar. This is just a sign that these stars are having unstable disks and accreting big lumps of matter just in the first 100,000 years of their formation. So to follow up on these outbursts, we want to come back and check up on them once a year, or maybe even more frequently than that, ideally. And the best way to do that is to use Sofia, the Stratospheric Observatory for Infrared Astronomy. And it's literally a retired passenger airplane where they cut a hole in the side of it and put a telescope there. So there it is, the Sofia telescope on the Sofia plane. You can ride on Sofia if you have time, if you get accepted for time to make observations. This is the Sofia control room. There are a lot of very highly skilled technologists and flight specialists there, and they just kind of want the astronomers to stay at their little table off to the side so we don't get in the way and interrupt too much. But the great thing about Sofia is it takes off from the desert in Los Angeles County every night and goes up there and can do mid-infrared and far-infrared astronomy without having to wait for a space telescope. So this is actually the flight path that we took for HUPS 223 and HUPS 383 back in 2016. So here's the west coast of Canada and the United States. Here's where it takes off from around Los Angeles County. All those pink regions are restricted airspace, and they don't tell you why those regions are restricted. So you can let your imagination run wild as to why you might not be able to fly over those particular areas. But we took off here, went out over the Pacific, and here, this was in February, so if you know anything about the constellation Orion, in February it's setting in the west early in the evening. So you look out the west side of the plane with the telescope. When we did HUPS 383, it's faint, so it had a long leg of the flight path. And then HUPS 223 is almost in the same part of the sky, so we can continue flying in pretty much the same direction. But that one only takes about half an hour to image. Then we looked at something in Perseus for some other astronomers, so this time we wanted to point sort of north. And then we came back down over the Canadian Rockies and the US Rockies and landed a little bit before sunrise. If you're lucky, the pilots will actually let you come up and sit in the cockpit and just sit in the back and promise not to touch anything while they land the plane. So that was pretty exciting, a pretty exciting experience. And this is what we see with Sofia. So these are the two fields, and this is HUPS 223, HUPS 383. Remember, HUPS 383 is very deeply embedded and faint, so it's barely a detection at all, but that's still useful. These purple circles show you other protostars, and then these little black dots are just image processing artifacts, just the way you have to do infrared astronomy. You get these kind of negative dots surrounding each of the point sources. But with the Sofia images, you can tell that the outbursts are still in progress. These both happened around 2006, and in 2016 they were still bright young protostars. So these seem to go on perhaps for decades, maybe even centuries. It's kind of interesting to be able to look at something that evolves over the career of an astronomer and to see how it changes. So I've showed you all this work with Spitzer and Herschel and WISE and Sofia. But next on the horizon is the James Webb Space Telescope. It's had a series of launch delays that you probably have heard all about. But the current target launch date is March 2021. JWST has 4 science themes: extragalactic science, solar system science. One of them is star formation, though. Because it's an infrared telescope, Webb will be able to see right through and into the massive clouds of dust where stars and planets form. So it's really helping us to understand our origins. So that's where we are with star formation in Orion. And I just wanted to wrap up by just kind of showing you this array of space telescopes, orbiting telescopes, airborne, and in some cases ground-based telescopes that we're using to really piece together how stars in Orion form. And by extension, if we understand how stars in Orion form, we understand how our own sun formed. So this guy here really has a lot going on that he probably doesn't even know about right within him that we can use to understand our own cosmic origins. Thanks.
All right, that was a fantastic talk, Will. So, I get the honor of asking the first question. So please tell me, what is your favorite ground-based observatory? As you work for Space Telescope Science Institute, I want to see your opinions on the other team.
Sure. So I do a lot of astronomy with the infrared telescope facility. It's on the big island of Mauna Kea. It's a 3 meter telescope. That's its diameter. And what's really cool about that is you can operate it even from like your laptop in your kitchen, and you can get all sorts of spectra to understand what some of these stars are really made of, and get a lot of details that you can't get just by seeing how bright they are. Yeah, Yeah, so the question was what was the originally anticipated launch date for Webb and what contributed to the delays? I don't remember what the original launch date was. The most recent launch date was, I think, last month, October 2018. And in this case, the delay was that they were performing a test where they started shaking Webb to simulate what would happen when it gets launched, and some screws came out, which is bad. So that's the most recent story. And I know there have been a series of similar delays that have to do with just the telescope and the instruments not quite being ready yet. But they'll tell you it's important to get these things right, so we'll tolerate the delays. Yeah, so he asked when we look at a constellation like Orion, what are the ranges of distances of the stars in the constellation? Now, your average constellation, the stars could come at any range of distances. They're just chance alignments. In Orion, though, those bright blue stars I was pointing to, and also all the young stars, are all part of a single kind of association of young stars. So they're all at pretty similar distances. I said they were maybe at 1,500 light years, but the range is really 1,500 plus or minus 100. Yeah, he was asking how do we know the time scale for how long it takes a star to form? So it's all based on looking at stars where the disk is gone or mostly gone, but they still look like they're young. And there are models that show you like how old a star with a particular surface gravity and a particular brightness and color is supposed to be. So we look at slightly more evolved stars, and then we start counting up the young stars. So we figure that if there are 1/4 as many stars with envelopes as there are stars with disks, then that envelope period must last about 1/4 as long as the disk period. So it's all sort of bootstrapping it back. We get sort of a general understanding of the timescale that way. Yeah, that's just a shutter to keep the mirror protected when it's not actually making observations. Oh, he asked about the flap on the upper left, that's the Hubble Space Telescope. I think so. I'm not quite sure of the technical details on that, but I think so. Yeah. He asked if there are improvements in the coolants on these telescopes. Um, yeah, people are coming up with sort of different ways to get around this problem. Maybe some sort of electronic cooling instead of having to carry a coolant around is something that's being explored. Um, there's also improvements being made in the possibility of going up and servicing the telescopes to add more coolant. But yeah, that's still kind of a limiting factor with far IR astronomy. No, he asked if the stars we're studying are similar to the sun in terms of their mass, and how would massive stars be different? And that's, I mean, mass is really the single characteristic that determines how a star evolves. So the stars that we're studying in Orion are primarily, we call them low mass stars, by which we mean maybe a quarter the mass of the sun up to slightly heavier than the sun. They all form in pretty similar ways. As you get more massive than that, the star's own radiation becomes so important that it really affects the process. So the star will still be accreting matter from its disk while it begins to lose mass because it's old and starting to blow itself apart. Things get very complicated with the massive stars. But these are the ones that have the most bearing on how the sun formed.
Okay, hey everybody. Um, so in my presentation, I would like to give you an introduction and an overview about planets orbiting other stars, so-called exoplanets, and why it's so important and interesting to actually detect and find them. But first, let's start with the night sky. So if you live in a rural area and you go outside during a dark night, you will see thousands of stars, and especially during summer months, you will see that a bright band crosses the night sky, which is the Milky Way, which is part of our galaxy, which consists of millions and millions of stars. And you might wonder if one of these stars is orbited by another planet. And there's certainly no spoiler if I tell you, yes, there are other planets around these stars. And our galaxy is made up by 100 to 400 billion of stars. And from the recent exoplanet surveys, we can estimate that more or less every star is orbited by at least one planet. So for our galaxy alone, it means we will have billions of stars. If we go one step further and look at our universe, where we have at least 100 billion of galaxies, up to 2 trillions of galaxies, we can expect trillions and trillions of planets in our universe. And with these large numbers, you might ask the question, is there a second Earth? Or an Earth-like planet, which is similar in size and mass, like our Earth? And the answer is a definitive yes. We have found planets which are very similar in size and mass than our Earth, but we cannot say at the moment how common they are. So the data are relatively sparse at the moment. And of course, the ultimate question we would like to answer is, do one of these planets show any signs of life? And by life, I don't mean necessarily aliens, but I mean biosignatures, which means molecules in the atmosphere of around these planets, which hint to a potential existence of life on these planets. And one of these important biosignature is oxygen. And another one, maybe you can guess it, water, exactly. And the other one? Close enough. It would be methane. And another very important one? Ozone. Okay. So, up to date, till today, we have discovered 377 confirmed exoplanets. And the majority of these exoplanets are not further away than 1,000 light years from our sun. And when we look at our galaxy from a top-down view, which is not possible, of course, but here in this artist's impression, we get a good representation of our galaxy, which is 150 to 200,000 light years in diameter. Our sun lies between two spiral arms, around 30,000 light years from the galactic center away. And 1,000 light years represents roughly this yellow circle you can see there. So it's a tiny, tiny fraction of stars where we have looked for planets so far. Before we detected or discovered exoplanets at all, people expected to, if there are exoplanetary systems around there, that they look similar to our solar system. And our solar system, as a quick reminder, looks something like this. This is an artist's impression. The scale, the size of these objects is to scale, but of course not the absolute distance from the sun. And in the inner part, you have these small rocky planets, Mercury, Venus, Earth, and Mars. And in the outer part of the solar systems, you have the gas giants, Jupiter, Saturn, Uranus, Neptune. But in 1989, there was a first publication. Where they presented, they measured continuously periodic changes in the star's position using the radial velocity method. And these periodic changes can be interpreted by an object which has a mass of around 11 times that of Jupiter orbiting the star. So it's quite massive. And they didn't call it an exoplanet at this time. Then nothing really happened, and 3 years later, at 1992, researchers found 3 Earth mass-like planets around a pulsar. And a pulsar is a very strange object. It's a neutron star, which is the result of a supernova explosion from a very massive star, much more massive than our sun. And you have to imagine that this neutron star has roughly the size of Baton Rouge, the diameter of Baton Rouge, and you compress the mass of the sun into it. So it's a very weird astronomical object. And then in 1995, there was a kind of a breakthrough where, again, with the radial velocity method, a planet was, and this time they called it really a planet, was discovered around a solar-type star, 51 Pegasi. And this planet had a mass of around half that of Jupiter. And the strange thing about this object was it orbited its star in 4 days. So 1 year on this planet is only 4 days. So we have first an object which is very, very massive, at least 11 times the mass of Jupiter. Then we have a planetary system where the star is not actually a star in a classical sense. And we have a planet which orbits the star very closely. Now, since when? Since the 90s, large exoplanet surveys started, and we found, as I said, almost 4,000 planets. And it was very surprising what we found. In this quite busy plot, you see some planetary systems which were discovered in comparison to our solar system. So here's our solar system with the orbits of our 4 innermost planets to scale, and the outer planets as well, which is kind of hard to see. And all of these are these exoplanetary systems, and the size of these disks represent the mass of these planets. And what you can immediately see is that the most of these systems we have discovered are very massive and very close to the star. So this has nothing to do with our solar system. So it's very was quite a surprise at that time. In addition, the planets we found are around evolved stars. So these stars are hundreds of millions or billions of years old. Like in our own solar system, our sun is 4.5 billion years old, and nothing happens in our solar system. So the planets won't change their orbital elements, they won't change their mass. The star will stay the same for another 5 billion years. And it's very hard to draw conclusions about the initial conditions when the planets formed, and to understand how these planets ended up at these close ranges to their host stars. And we do not know what was the chemical composition of their environment and so on. Okay, now you can say, okay, you have all these big telescopes, look at young stars. And that's actually what we are trying to do. And for that, we go back to the Milky Way, and you can see these dark filaments, these dark clouds, which contains a lot of gas and dust. And these are the places where where new stars are born. And thanks to Will, we already know how stars are formed, so I can skip quite a lot of it. So I go to the stage where the star is born, and the remnant material of gas and dust is distributed in a disk around the star itself, and which is what we call a circumstellar disk. And in this disk, planet formation is happening. You have small dust grains, micrometer-sized dust grains. They eventually collide, stick together, and grow in size. And they grow from micrometer to centimeter or inches, or whatever your preferred system is, to yards, okay, kilometers, and so on. And if they are massive enough, like several times the mass of Earth, they control their environment gravitationally and can collect a lot of gas and dust in a very short time. And this is basically how you create these gas giants. And at the end of this process, you're left over with your planetary systems. So you see, planet formation is like a piece of cake. You mix flour and sugar. Eventually, these components stick together, and you get a solid body out of it. Now, the technological advance in the last decade allowed us to look at these circumstellar disks in very close detail. And here are very nice examples I would like to show you. The star itself, which is always in the center of this image, is not visible because the stellar light would overwhelm the entire image and you wouldn't see the faint structures. And you can see that these disks show spirals, rings, gaps, and these features are thought to be signs of ongoing planet formation. So, how can we find now a young planet in such a disk? Well, one method is the direct imaging method. So we simply take a picture, which is not as simple as it sounds, because you have to imagine that the planet itself is 1 million times, 10 million times, or even 100 million times fainter than the star itself. So when you look with a big telescope at a star, the star overwhelms everything in your image. You will never be able to see a planet unless you block its light with an opaque mask, what we call a coronagraph. Another problem is that any star is very far away from Earth. That means that the apparent angular separation on sky is extremely small. So a typical value is a millionth of a degree. So you want to observe something which is a millionth of a degree away from a bright star, which is 100 million times fainter than this star. So as a comparison, when you are bored during the weekend, you go to LSU Tiger Stadium, you take one of these floodlights, you mount these floodlights on the state capitol building in Baton Rouge, 2 inches next to it, you set a candle, you drive to New Orleans City Park, try to take a picture of this candle by removing the light of a floodlight. And this is roughly the difficulty we have to deal with. But another difficulty, of course, is atmospheric turbulence because of different temperature layers in the atmosphere. The images are always blurry and unstable. And if we look with a large telescope at a star, the star is just a giant blob, and you cannot see really anything around it. And that's why astronomers have something which is called adaptive optics, which can correct for these atmospheric turbulences. And if it's switched on, you can see that this large blob is actually made out of 3 sources. So with that, we can actually increase the spatial resolution and also increase our sensitivity, which means we can observe much fainter objects. So these are the 2 ingredients needed to perform direct imaging. Now, this is a very popular or famous example of a direct image exoplanet systems, HI 8799. The star itself is hidden behind this mask in the center, and it was found that this planet is orbited by 4 planets. And if you take a lot of images over a long period of time, you can actually also see their orbital motion. Now, another system I would like to introduce you to is PDS-70, which was called Baby Planet. I will comment on this. PDS-70, the star itself, it's a very young system. So it's only 5.4 million years young. It's a little bit less massive than our sun, and it's 370 light years away. And for a long time, we know that it's surrounded by a circumstellar disk, and that this disk has a large gap, so an area which is void of gas and dust mostly, so which is a sign of ongoing planet formation. So it's an interesting target. We looked at it, and in 2015, May 2015, we found a signal right here. So the star is again hidden behind the mask. Here you see partially the circumstellar disk, which looks a little bit weird because of image processing. But with one image, you can never be sure if it's a real signal or if it's an artifact or anything else. So we got another data set a month later, a year later, at a different wavelength range, which means at a different color of light. And when we got another 2 data sets with completely two different instruments at 2 different wavelengths. And after painful months of analysis, we were very confident that this is a planet we detected here. So in early 2018, we went back and invested quite some observing time to make this so far unique and very stunning image of a young exoplanet orbiting inside the gap of a circumstellar disk around this young star. So here you can see beautifully the circumstellar disk, this large gap, this area which is void of material. The planet is here, the star is hidden. From our analysis, we know that this planet is around 5 times the mass of Jupiter. It needs 120 years to orbit its star. And the fascinating thing about this is that we also discovered that this planet is still accreting material. So it still collects dust and gas from its surroundings and still grows a little bit in mass. And this is a very unique discovery so far, and it will be a prime object to test our theories and models. And for example, we can check, okay, how does this planet influence this circumstellar material? We can, for example, closely investigate the properties of its atmosphere and so on. So the media liked it, and a lot of A lot of media called it baby planet. Even mighty, here it is, mighty NASA called it a baby planet. Um, I would say it's a very young object, but something which is heavier than 5 times the mass of Jupiter. It's hardly a baby. So at the end, I would like to leave you with this image, which is one of the most iconic images in space exploration, which was taken by the Voyager 1 space probe back in 1990 at a distance of 3.7 billion miles, which is roughly the orbital distance of Pluto. And what you see is basically noise and some sunlight rays hitting the camera. And do you see something else in this image? Yeah, so you see here something, it's not a dust speckle on the projector, but this is actually Earth. And to quote a little bit Carl Sagan here, which I really like, is that every person you know and every person you ever knew and every creature which lived on this planet and every book which was written and every technological advances human mankind made and so on and so forth happened in this one pixel. And this shows one thing first, how insignificant actually humanity is. But also it demonstrates that we need to search and find and characterize other planetary systems to understand how Earth got its place in the solar system. Thank you for your time.
All right, Andre, that's a fantastic talk. So, I've got a question for you. And we actually had a donation more on this earlier, and that is, are we going to, in your opinion, do you think we're going to detect bio or technosignatures outside the solar system first, or do you think we're going to be able to directly detect some sort of biosignature here in the solar system?
It's a kind of a race in a sense, because there are missions which try to detect life on other bodies in our solar system. So, which means bacterial life or whatever it might be. So, because one of or several moons around Jupiter or Saturn have conditions which might be suitable for life, not like humans we know, but if the James Webb Space Telescope launches at some point, hopefully we might be able to answer this question by then. Or with the construction of EELT, the Extremely European Large Telescope, it's a 40-meter telescope, or 55-yard telescope, or the American 30-meter telescope, which have the spatial resolution and the sensitivity to actually probe the atmospheres of these Earth-like planets. Who will be first? It's hard to say. It also depends probably a lot on funding. So I would say outside solar system will be first. But it will take a while.
We open it up to you guys.
Yeah. Yeah, not many. The question was, how many of the planets we have found so far would have the conditions to sustain any life? The majority of the planets are very massive, very close to the star. If they're very close to the star, there's a lot of radiation which burns everything away. So it will be very hot, or they are very far away, so it will be very cold. from the handful of Earth-like planets which are detected by Kepler, which lie in the habitable zone, which means the planet's distance to its host star is just right so that water can be liquid. Yeah, I would say it's a handful. It's not much, but that's why we need the statistics. So we need to find these systems. And of course, it's always easier to find heavy planets because they create the strongest signals on our detectors. Earth-like planets, if they are 1,000 times less massive, they are much harder to detect. So, yeah, it will take a while to answer this question better.
So actually, I don't know if you guys have heard recently, but NASA lost two telescopes. We lost one out in the asteroid belt, and we also lost Kepler, which is an exoplanet hunting telescope. And if you guys are really interested in helping out real functioning human scientists, you can go to Planet Hunters and you can help identify potential exoplanets with the Kepler data. And Emily, MC's Space Princess, that's actually part of her research here. So she would really appreciate if you contributed to this research. So, little fun asterisk onto that answer.
Yeah. So the question is if we have not detected any signals of life because the universe has not existed long enough. Yeah, that's a very philosophical question. So I would say at the moment it's simply impossible. So if our current physics work, and the current physics sets the velocity of any object, the maximum velocity an object can reach to the speed of light, when it's very hard to reach other worlds. So, I mean, we started radio transmission 70 years ago or something like that, which was strong enough to escape Earth's atmosphere, which is now in interstellar space. So it's 70 light years away only. That's nothing. So, there's just a couple of stars. So, and of course, there were the SETI projects which look for these alien signals and so on. And there are articles which basically say if there would be an alien life form and it would try to contact us, we wouldn't understand it. It would be too complicated. Yeah, but it has its limitations because distances are large, and if you are limited by the speed of light, and at the time the signal was sent, very far away, it will be very weak. You have to know at which direction you have to look and so on. So it's a very difficult thing. So we are far, far away from this. So finding planets which are Earth-like, which have biosignatures, which hint to the potential existence of life, is the very first step in the future. We have to go for it. The question is, how many astronomical units is the planet, the baby planet, away from its star? An astronomical unit is the distance between Earth and Sun. And because it's a very large distance, we shorten it to a so-called astronomical unit. And for this baby planet, it would be 22 astronomical units, which roughly compares to the orbital distance of Uranus or Neptune. Neptune. Yeah, around 100 years, something like that. So it's relatively similar, roughly, as a comparison. I do not understand you, sorry. Right. The question is, if a planet is so away from the star, so 22 astronomical units, what keeps this planet so hot? And because the planet is so young, it's still in the formation process, which means it's still contracting and releases a lot of gravitational energy, which still heats. That's why for the direct imaging method, we are looking primarily at young stars because they are still luminous and the contrast ratio between the star and the planet itself is much more favorable. The question is if it's possible to observe exomoons around these exoplanets. In principle, yes, because they introduce the same signal like a planet, but it's orders of magnitude weaker than that of a planet because the moon is several orders of magnitude less massive. So the sensitivities might be at the edge. There was a publication half a year ago or so which claimed to detected exomoons, cannot remember properly. There are methods like gravitational microlensing where you could, in principle, detect these exomoons, which is a very sensitive method, but so far, not to my knowledge, this was done unambiguously.
So you all come from wildly different places. Where is your favorite place that you've worked?
Yeah, for me, it's definitely the Paranal Observatory in Chile. It's a very fascinating place, 2,500 meters above sea level, driest place on Earth, big telescopes, great instruments. So that was definitely a great time for me.
I think my favorite place to work was when I was a grad student at UMass in Western Massachusetts. There's a great local brewing industry there. You guys are all into that sort of thing. In Western Mass, everybody's sort of easygoing, friendly. It's a really nice place to check it out if you ever are on your way to Boston and want to stop in Amherst or Northampton or something.
I'd have to say the most interesting place that I've worked is Mount Wilson, which I did not find the air to be all that thin. I don't know what Tyler was talking about. Mainly because we didn't use the Hooker telescope, which is an interesting name for that telescope, but which is the 100-foot telescope. I used the Char array, which is 6 telescopes, which you combine the light to get the resolution of a much larger telescope. Well, most interferometrists, like Tabby Boyajian, they use 2, maybe 3, maybe 4 telescopes at once. I used all 6, meaning that whenever I decided that I was going to do some observing, there was a whole bunch of grumbling because nobody else could do any work except for me. So I guess that's probably my favorite place to work.
Wait, do I have to answer this too?
Sure.
I think my favorite place to work short term was I actually got to go up on Sofia, that aircraft that Will mentioned in his talk. So I did some work on there studying the kinds of protostellar outbursts that he was talking about. And it was a really weird experience because he mentioned it's like a 9-hour flight. You're over an ocean. It's really, really cold in the airplane and it's really loud. So you can't actually talk to each other even if somebody's sitting right next to you. You have to talk to them on a special frequency on a headset. So really, really weird. But I wouldn't trade it for the world. It was a really unique experience, and I'm glad that I got to have it. So That's probably my favorite place I've worked short term. Long term, actually, my favorite place was a community college where I taught for a while before I went to graduate school. It was really relaxed and fun. I made a lot of friends there, so I think that counts. Other questions? It is actually a hole in the fuselage. It's sort of weird. I mean, that's why it's so loud and so cold. The only thing that's really keeping people away from that big hole is like a little section of rope that sections off where the telescope is from where everybody sits and where science ops are. Very safe. Oh gosh. So the question was, what is our favorite planet and why? Do any of you guys want to go first on this? Oh, me? I think I actually have to go with Jupiter on this. I know that's a little boring. I mean, I do exoplanet science, so I have like thousands of them to choose from. But honestly, Jupiter, because if you actually like spread out, this is going to be like the stupidest reason. But if you like took like the surface of it and spread it out, it would make the best carpet. I thought that for years.
Well, yeah, there's Pluto. I do like Pluto. It has a heart on it. Actually, I'm going to go with a collection of planets, the planets around TRAPPIST-1, mainly because of just how unique of a system it is, where you have so many planets so close together. They're all probably tidally locked, and I'm very interested in the dynamics of that system. So.
So as long there's no other planet around serving beer, I stick with Earth.
I think we need to look up Mars some more. Mars is there might have been life there in the form of bacteria or something. There seems like there maybe have been liquid water there at some point in the past, or maybe even in the present. There's just a lot of mysteries still in Mars to find out what was going on there and what might still be happening. I guess I've got the mic, so I'll keep talking. When I was a kid, that was right about when Voyager 1 and Voyager 2 were visiting the gas giants in the outer solar system. So my mom took me to the library and we found some books with images from Voyager 1 and 2, and I thought it would be kind of interesting to learn more about what was going on out there. So for me, it started way back.
Well, for me, it was boring, the boring path. So we still had astronomy in school, and I always found the physics very interesting. And at some point, I took the binocular of my dad, looked at the skies when I was a young teenager, and since then I'm sticking with astronomy.
At the beginning of my 7th grade year, I really wanted to be a geneticist. I don't know why, I just did. And then I was looking through my science textbook, and my science textbook had essentially these pages, highlights in astronomy or highlights in whatever science. And there was a page highlighting the work of a woman cosmologist. I think it was Vera Rubin, but I couldn't sort it. But whatever it was about what I read convinced me that I really wanted to be a cosmologist. Later, I realized that cosmology was far beyond what I could comprehend, but I still stuck with astronomy. So that's essentially where it stuck. Seventh grade.
For me, I guess it's sort of like Will, in that it started when I was a kid. Um, so my dad used to be really into astronomy. He would get Discover magazines all the time, and anytime there was an article about black holes, I would insist that he sit down and read it with me. And I would read all. I mean, I was like 10; I couldn't understand a word of it, but I really thought it was super cool. Black holes, what's in a black hole? How did the universe start? How is it going to end? Lots of cosmology questions really fascinated me at that time. And I went through a period where I thought maybe a more practical career might be as an earth scientist or a geologist. And then I thought maybe meteorology. And then I thought astronomy. And I mean, my interests went from the ground up and it just stayed there. And I never got over astrophysics. So that's what I do now.
Just as a warning for the young people here, if you want job security or long-lasting contracts, don't do astronomy.
Agreed. We have one more question over here. Let's go ahead. What? Okay, this is a really interesting question we've never had. The question is, if we were all to become famous astronomers, what would we want to be the thing that made us famous? Do any of you have an immediate answer for this?
So, we don't do astronomy because of money or to become famous. Yeah. I mean, there's this one discovery in your lifetime, which is usually by pure luck you make, which causes a larger media interest and stuff like this, and you're a little bit more known in the community. And I mean, it depends on the field. For me, of course, it would be aliens.
Ditto.
Well, I had a suggestion from someone in the audience that I really can't refuse, and that is if I discovered that the Earth was flat. That would truly be quite the discovery. Too late? Uh-oh. Oh, maybe I missed the boat on it. To be honest, I mean, what Will mentioned in his talk, like finding HOPS 383, that was work that I did as an undergraduate, and that paper has already been cited so many times by other astrophysicists. Like, that to me is a degree of fame already that I could not have comprehended I would achieve. Like Andre said, this isn't really something that people do to become famous. So, really, I'll take anything.
We are humble.
What?
We are humble.
We are humbled, yes. Will, how about you?
There was an astronomy professor where I was an undergrad at the University of Toledo who said stars are fascinating things, but people are more important than stars. So I think that if I were to be well known as an astronomer, it would be for like having an effect on students and other people to understand something about the universe that we're a part of, and maybe understand something about themselves from what it's like to discover things and to make progress on these problems that are facing humanity. So it's like the influence on other people, I think, is for me what drives me to keep doing astronomy. Yeah. There are definitely astronomers that specialize in each of them. You can go find the Pluto people and ask them if Pluto counts as a planet, and you have to have to have some time on your hands, I think, to listen to their answers. But yeah, definitely. People are specialize in each planet. Saturn and how Saturn got its rings and how long those rings are going to last is a pretty exciting field of study to the planetary scientists. So yeah, definitely.
I just want to add one thing onto that, and we actually just got confirmation today that in March we're going to have somebody here who studies specifically Mars. So if you're interested in, yes, it's Matt Damon. No, it's not Matt Damon. I'm sorry. We can't get people that famous to come and talk at AOT yet. But yeah, so stay tuned and keep coming to Astronomy Tap if you want to hear somebody talk about Mars at least.
Actually, I have a kind of an interesting anecdote towards that. When I was a grad student at University of Florida, my department chair, who was a cranky Brit, who I won't name, had the habit of sitting in the back of the room and sleeping and snoring very loudly during colloquia. Well, one of the colloquia was a gentleman who was speaking about Mercury. Well, my department chair woke up somewhere along in the talk, and his first question to the man was, "Why are you studying this? It's a dead rock." So, well, yes, there are definitely people who study different, like Mercury, Venus, and whatever. There are kind of they're opposites of the astronomers who kind of have this sort of wonderment as to why you would study such a thing. So I don't know. I just kind of looked at him in shock at that moment.
Yeah. So there's wonder about the pure size of our Milky Way, and I mentioned that it's 150,000 to 200,000 light years across. And these are just numbers. Nobody can imagine these dimensions. Um, and it's you just have to live with it. There's no other explanation than it's the universe is very large, unbelievable large. So is our galaxy, and even our own sun is so heavy, so large that we cannot imagine, um, the pure mass of it. You mean the number of stars compared to the size? Yes, it is, and it's just a number, and you just calculate with it. You do not try to think about it.
I don't know if I understand your question. Stars within our own galaxy? I thought it was actually fairly well understood.
No. So the number of stars in our galaxy is around 100 to 400 billion stars. Why is there such a large range? Well, if you remember the image of the Milky Way, that's all what we see from our galaxy. We cannot fly out of our galaxy because our galaxy is 3,000 light years thick. So it's impossible to fly out, look down, count all the stars. So this is a statistical process. You cannot see all the stars on the other side because there are a lot of dark clouds absorbing all the light from all these other stars, which is actually what Will showed, that these are embedded in these clouds and so on, and the stars which are behind it, this light is blocked. So this is a statistical approach, and there's always a certainty, and you will never get a precise number, but the order of magnitude is very precise.
The Delta Quadrant in Star Wars, they didn't, or Star Trek, they didn't know much about it, so because it was so far away. Yeah, he's asking like, why do planets line up sort of in a flat plane? And it's because when they're forming, the cloud's collapsing, but it's spinning a little bit, so it forms a disk. And the planets that form out of that disk are all going to be in the same plane. So I think in general, the exoplanetary systems that have been discovered are like that, as far as we can tell.
Yeah. There.
Oh, you're probably more of an expert on it than I am.
There are exceptions, as always, which is mainly or very likely due to gravitational scattering or something like that they get misaligned. I mean, even the planets in our solar system are not perfectly in a plane, so there's a huge variety. So, but yeah, because of conservation of angular momentum, which is the big word we have to use for this here, these things are these rotating things. Everything which is rotating has some angular momentum. So things are distributed in the plane, and that's why it always roughly looks like this. I mean, if you go outside, I think Neptune is quite misaligned. They are not on circular orbits, they are on eccentrical orbits, and this is all due to gravitational interaction between these bodies, which can lead to misalignments.
Could you repeat your question?
Theology?
Yeah.
So the question is, based on the things that we've learned and witnessed as scientists, how has that affected our views on theology? So, me personally, I was more or less agnostic even before I started studying astronomy and astrophysics, and that hasn't really changed very much. I guess the more I get into science, the more I think that the scientific method is valuable to me personally. My belief system really relies a lot on the scientific method. And it's just asking questions and critically thinking about the things that I experience and the things that people tell me. And that includes theology. So I guess it's one of those things where I'll never stop asking the question of whether or not there is a God, whether or not theology has deeper meaning, but it may or may not ever be proven. But I mean, the thing that really counts is that I'll keep asking the question, I think, and that's been born out of science for me.
The answer for me is not at all. I don't believe that science and theology have really a place in the same room. They ask completely separate questions, and they deal with completely separate issues, and they really do not. As far as I like to look at it, there are two sides of a coin. Science is going to tell you, how things came into being. Theology might tell you why things came into being. So that's how I look at it.
to comment on this, I totally agree. Um, the important thing in science is that you can repeat the experiments. That's a little bit hard to do in theology. So, um, yeah, I have nothing else to add to it.
I think if you look at the writings in different religious texts about the origin of the Earth and the origin of the universe, you see people in sort of ancient times trying to use nature to say what their God was like. I think that's a different goal than trying to say literally how things actually came into existence, which is what scientists are interested in doing. So it is sort of like different questions that people are trying to answer. And I think you run into trouble when you look at religious texts and try to take those as literal descriptions of how things came to be. Right. Yeah, I mean, if you look at if you look at what we know about the universe and you're not driven to deep questions, then you're probably not you're doing something wrong.
Just a quick little, again, anecdote on that. One anecdote or one paraphrase quote, I guess, from Galileo is that Galileo basically said that the Bible should be believed in total, excuse me, until science proves it to be false. So believe the Bible until science tells you otherwise. Wow. No, it just reminded me of like it just reminded me of the quote by Galileo.
Talk to us later if you want to continue this discussion.